In the first part, we presented the general linear inverse problems, like the blurring problem, and discussed several theoretical approaches to achieve a solution. First, we described the least squares approach, using an estimator to minimize data error. Then the Tikhonov regularization, another one with a quadratic penalty in the objective function. And later, an interesting L1 regularization, which essentially would indirectly induce a sparsity in our solution, ideal for image representations in the wavelet domain. However, as it turns out, these approaches break down for large-scale dense matrices. And since interior point methods can't be used in these scenarios either, the development of simple and fast gradient-based algorithms was needed. In order to continue building towards VISTA, which will be part 4, we first need to discuss ISTA and its slower rate of convergence. ISTA works in a very similar way to gradient descent, essentially using information from the function at an approximation xk to find the next better approximation xk plus 1. Initially, the idea is presented as a simple gradient descent followed by a shrinkage operator, tau. Next, in part 2, I believe, the model was generalized so that it would apply to functions with some non-smooth component. That example over there is the norm one, but then it's generalized for any non-smooth function gx. For this, the authors used the proximal algorithms, which we explored in our first paper, I believe. And step by step, they showed the sequence formula that you can see under total generalization, where L plays the role of the step size. All in all, the ISTA algorithm reduces to this box statement on the left. First, we choose our initial vector, x0, as a guess, and we subsequently apply the prox operator, which we defined earlier, to obtain the next estimate in the sequence. The way I see it is this: if you want to minimize the red function, regardless of whether it is a perfectly smooth one or it has some jumps, corners, you first create a local approximation that is easier to minimize. And in that point, wk plus 1 on the picture that minimizes the green, you continue doing the same over and over. You make another local approximation with the blue curve, and gradually you can see how you advance towards the minimizer of the red. So when you have the Lipschitz constant for the gradient of the function, the basic iteration is that straightforward. They still call this L the step size, but in the context of what I just explained, I would rather understand L as somewhat of a factor that determines the quote-unquote curvature, the local approximation. But anyways, carrying on, as you may have guessed, the drawback of this approach is that the Lipschitz constant is not always known or computable, in which case we need to use the backtracking algorithm. This algorithm on the right is essentially the same, with the exception that in each step, intermediate calculations are necessary to find the appropriate value of Lk, namely a value of Lk that satisfies the inequality below, in a way that allows us to use lemma 2.3 and guarantee that f of xk plus 1 will be smaller than f of xk. I mean, we're minimizing it. And you can probably see now why these gradient descent methods are so slow. They have loops within loops and it can take forever. Now, in order to formally analyze the convergence of these algorithms, the authors present some of the current knowledge in the form of a theorem. If xk is a sequence of estimations, then it can be proven, mainly invoking lemma 2.3, that the difference between the images of the kth approximation and the actual solution x star is actually always less than the distance squared between these two divided by twice the number of iterations and scaled by some factor alpha representing the step size. In essence, this result formally tells us the number of iterations needed to obtain an answer within an error interval of width epsilon. Earlier, we informally reasoned a rate of O1 over k, but now we can see that the number of iterations for an epsilon optimal solution is at most C over epsilon. This can be seen, using the theorem and applying the arbitrary condition uh, that the difference between the images has to be less than epsilon. We essentially solve for k and obtain c over epsilon, where c is that quantity expressed below. Qualitatively, the further you take your guess, the more iterations you will need. And the larger your error interval, the less number of iterations, because you will converge faster. In the next slides, I think Adrian will explain the paper's proposed way of improving the complexity result to O of 1 over k squared.